Okay, good morning. So I'd like to continue our discussion of the Jacobian. And today we're going to start, hopefully by the end of the lecture, we'll start seeing some real examples of how the Jacobian is useful. Okay, so we'll try to get to singularities. But before we do that, let's review all the results on velocities that we covered, because I know it can be kind of confusing. Okay, so we have a lot going on in terms of velocities, what's what. Okay, so let's set things up by drawing a picture. Okay, so here's our fixed frame, which we label S. Here's our moving frame, which we label B for body. Typically, we associate this with a moving body. Okay, and so we have this transformation T, and normally we write TSB, but because the notation might get cluttered, for now we'll just write this as T. Okay, and this is a rigid body transformation consisting of a rotation matrix and a position vector. Okay, and this is, like I said, it's moving. Okay, so if it's moving, we can associate it with a velocity, actually two velocities, a linear velocity and an angular velocity. So we know that the linear velocity will typically be, well, actually will always be, okay, tangent to the path. And it's going to have some angular velocity. Okay, so maybe something like that. Okay, and the goal here is to try to derive from t and its derivatives the angular velocity and the linear velocity. Okay, so here's what we have so far. Okay, first result is that if we take r, okay, take its time derivative, multiply by the transpose, which is also its inverse, then what we get is a skew-symmetric matrix, okay, omega s. And here, omega s, okay, is a three-dimensional vector. This is just the angular velocity expressed in the fixed frame S. Okay, so this is the angular velocity expressed in the fixed frame S coordinates. Okay, the other half of the result is that now if we reverse the order and multiply r dot by r transpose from the left, we get another skew-symmetric matrix. Okay, let's call it omega b. Okay, and this omega b happens to be the angular velocity, but now it's expressed in the b frame coordinates. Okay, so let's write up here. It's the angular velocity expressed in B frame coordinates. Okay, so this part I think we're okay with, right? We spent about 2 lectures going over this. A couple more results. Okay, here's the third one. Now, if we take the entire t, okay, take its derivative. Actually, let's do t inverse t dot first. Okay, if we do that, what we get is we get omega b here, okay, and v sub b here, and and 0, 0 here. Okay, so omega b is as before. Okay, it's the angular velocity expressed in the body frame. V sub b, it's a three-dimensional vector. Now, what is this? This is the linear velocity, okay, of the moving frame expressed in b frame coordinates. Okay, so this object is moving. Okay, it has a linear velocity. Okay, the origin of the frame is moving with a certain linear velocity. Okay, v sub b, okay, is this velocity expressed in the b frame coordinates. Okay, that's all it is. All right, but I'm going to write it in a slightly unusual way. Okay, so this is the linear velocity of the B frame origin. Okay, expressed in B frame coordinates. Okay, so I think it's pretty clear what VB is. Okay, now if we switch the order, T dot T inverse. Okay, we get another matrix, similar structure as this. Okay. So this time now we get a skew symmetric matrix here, which corresponds to omega s. And we get some vector v sub s over here. Okay, so omega s is as before, same definition. Okay, so v sub s, three-dimensional vector. Okay, so this is where it gets kind of strange, you know, if you're seeing this for the first time. This is, so let's write it down. This is the linear velocity of the S frame origin okay, expressed in S frame coordinates. Expressed in S frame coordinates. Okay, so if you compare the statement of v sub s with the statement for v sub b, okay, you see there's a certain symmetry to it here, right? Replace b by s here and you get v sub s. All right, so what does this mean? Okay. So let me modify this drawing a little bit. Okay, so there's a B frame here. Okay, pretend this frame is attached to some moving body. There's a moving body. Okay, let's pretend this body is really big. It's infinitely big. It's as big as the universe. Well, maybe big as the Earth. Okay, so let's blow it up. Okay, so it's going to be this huge body. Okay, now it's this moving rigid body. Okay, and it's infinitely large. Infinitely large. Okay, so as this body moves, let's think about this point here, right here. Okay, so think of this point as belonging to this large rigid body. Okay, as this body moves, this point will also move. Okay, so what is v sub s? V sub s is the velocity of this point expressed in the S frame. Okay, as this body moves, sub s. Okay? All right, so the way to see that is to just look at the formula for v sub s. Okay, so v sub s, do the calculation yourself. This is just going to be omega s minus omega s cross p. Sorry. P dot minus omega s cross p, which we can write in this way, omega s cross minus p. Okay, so if you think about what minus p is the vector from, p is what? P is the vector from the s frame origin to the b frame origin. So minus p is the, right? It's the same vector in the opposite direction. Okay, so that's minus p. Okay. So the easiest way to understand this interpretation is think about what this equation means. Okay, so this is where we were. Now, if we want to, so the message that I've been trying to deliver to you from early in the course is that let's try to think six-dimensionally. Okay, let's not separate linear and angular velocities and treat them as different things. If possible, let's combine the two and think about things six-dimensionally. Okay, so to do that, we define this six-dimensional vector. Now we're going to lump omega s and vs together. Okay, call it some capital V sub s. Okay, so this is a six-dimensional velocity. Okay, now we use so we need some terminology. Okay, so we're going to call this a spatial velocity. Okay, we'll talk about the notation a little more. Okay, but just want to throw it out there for you now. Okay, so V sub s is defined this way. Now, if you see me write V sub s inside square brackets, okay, that means this is a 4x4 matrix version of this. Okay, in other words, I'm writing it this way. Okay, it's 4x4. And in fact, this is just T dot T inverse. Okay? All right, so we can do the same thing with V sub B. Okay, so let's stack omega b and small vb into a six-dimensional vector. Okay, we'll call it large V sub b. All right, and chuck. Okay, this is again the 4x4 matrix version. Okay, which, as we verified earlier, it's just T inverse T dot. Okay. All right, so the relationship between V sub b and V sub s, okay, we can write in a number of ways. Okay, let's start with the matrix version. So if we want to get V sub s from V sub b, what would we do? We would take V sub b, which is T inverse T dot, okay, multiply on the left by T, and multiply on the right by t inverse. Okay? All right, so if we want to get VB from VS, well, just move the t and the t inverse over to the other side. Okay, we can do that. If you want to write this in vector form, okay, write it in vector form. V sub s, okay, which is omega s V sub s. Okay, this is in fact going to be equal to R PR R0 omega b V sub b. Okay, so I said earlier that to keep the notation simple, I'm going to just write R instead of RSB, okay, and P instead of PSB. Okay, but here's a good time to maybe just instead of writing R, write RSB. Okay, so let's do that. RSB, SB, PSB. Okay, so use the full notation. Okay, and you can verify this. We already did this. I'm going to give this matrix a name. This 6 by 6 matrix. Okay, this is going to be add TSB. Okay, inside square brackets. Okay, so general idea. Anytime you see square brackets around something, it's going to be a matrix version of that, a matrix version. Now, the matrix version can be 3 by 3, or in this case, okay, 4 by 4, or in this case, 6 by 6. Okay, but this square brackets, it's a tip-off. It means it's a matrix. Okay, so it's add TSB times, what is this? This is V sub B. All right, so V sub S is add TSB V sub B. So this is also not too hard to remember. Okay, it's the indices, right? So if you see repeated indices like in B here, they cancel, and you're left with V sub S. All right. I'll write this notation. Sometimes I'll also write this as add TSB VB. Okay, so you're probably aware of this idea of thinking of a matrix as a linear mapping, a linear transformation. Okay, so it's this linear transformation acting on this vector V sub B. Okay, so it's something that takes as an input this V sub B, produces V sub S in this way. Okay, so this notation, okay, means the same thing. All right. Okay, now if we want to go the other way, not too hard. V sub B is add TBS V sub S. Okay, just replace the notation. B by S and S by B. Okay. All right. So I think that's where we were last time.